Okay, dear students, in the last class we have to discuss about the some problems of the group's properties and solve the using this. And now in this class is also we have to discuss some uh, more problems, and then we have to complete this section of the uh, group section of this. So let us start with the first problem. So let if two elements A and B are in a group G commute, then show that A inverse and B inverse commute, A inverse and B commute, and A and B inverse is commute. So we have a given is any two elements A and B are the element of a G. If A and B are the element of a G, then every element has an inverse. So we have to just say that A inverse belongs to the G and B inverse is also the element of a G. And we have to show that, we have to try to first, the second one is we have to show that A inverse and B is commute. Then we have to show that A inverse B is equal to B of A inverse. So we have a given condition is this: A and B are commutes. So we have AB is equal to B of A is equal to satisfy this. So we have to just write multiplied by A inverse into this. So AB is equal to A inverse B of A. Now using the associativity conditions, we have a B, we have a inverse B into A. Then identity of a B is equal to, we have A inverse B into A. Now we have this is a B, and B is equal to A inverse B, and we have to associative by A. Now we have to write multiplied by this A inverse. So we have a inverse B. Now we have a inverse. So B A inverse is equal to A inverse B, and this is equal to identity. So we can say that B of A inverse is equal to A inverse B. So satisfy this means A inverse and B are commute. So we can show that this is very true, this one. Similarly, we can show that A and B are also A and B inverse is also commute. Let us try. We have to just say that we have a AB is equal to BA is there. Then we have to show that A and B inverse is equal to B inverse is equal to A. We have to show that A and B inverse are commute. So we just say that A B inverse, we have to write B A B inverse. So we have A B inverse is equal to B A B inverse. Now this again is identity. So you can write B A B inverse. Now again A is equal to B A B inverse. Now we have to add B inverse A is equal to B inverse B, and we have a AB inverse is again identity, and then we have a AB inverse is equal to AB inverse. So we have a B inverse A is equal to the same as a AB inverse is there. So we can say that in this case also we have to say that this conditions hold. So we prove this these two, and then I leave this one first one for you as the exercise. Try to this thing. So let's move to the next exercise. We have to say that show that a group G is abelian if and only if A B A inverse is equal to identity. So one way we have to just say that suppose A B are the element of a G. So we have a given A B A inverse B inverse is equal to identity. So this can be written as A B A inverse B inverse. We have to multiply it by B, then A B. So this can be written as A. We have a B A inverse, and then we have to using the associativity condition B is equal to this is B. Then we have A B A inverse, this is equal to, you have a identity, and then again we have a B A inverse is equal to B. Then we have to multiplied by this is A. So A B A inverse A, and then B of A. Again this is we have a AB identity is equal to B of A, and this implies that AB is equal to B of A. So then we have to show that if A and B, this condition is hold, then G is abelian group. On the converse part, we have to giving the AB is equal to B of A. If AB is equal to BA, then we have to show that AB, A inverse, B inverse is equal to this satisfy. So because A is the element of a G and B is the element of a group G, so this means A inverse is the element of a G and B inverse is also the element of a G. So this can be written as AB. We take A inverse is equal to B times A inverse. So this is B times of identity, and this can be written as A B A inverse is equal to B. Then again we write A B A inverse, B inverse is equal to B into B inverse, and B into B inverse is equal to, you have given the identity. So we have to show that A B A inverse B inverse is equal to identity. So we have to clearly show that these two conditions is hold. If so, if G is abelian, if and only if this condition is hold. Let us try for another problem, and this problem we have to collection is a show that the set Q of all rational numbers other than 1, so except 1 is an abelian group with respect to the binary operation A composition B is equal to A plus B minus AB for all A and B belongs to Q. So we have to first show that the closure property, for a closure property means A composition B is the element of a this. We know that A and B are the element of a Q, so A plus B is also the element of a Q, and A and B is also the element of a Q. Sum of a two irrational number is a irrational number, product of a two irrational number is also is a irrational number. So we can say that if these are the things, that this whole thing is belongs to Q, and also because A and B all the rational numbers other than 1, so this cannot be equal to 1. So this means this whole thing is belongs to Q, means this implies that A composition B is the element of a Q. So first condition is the satisfies clearly, then associativity we can trivially satisfy A composition B composition C, means we can write in the form of a, if this A composition B, we have plus C minus A composition B into C, and then we have to apply again this operation. We have to write A plus B minus AB plus C minus ka we have to write A plus B minus AB into C, and then similarly the other condition is A composition B composition C. So this is trivially satisfied for a associativity condition is also hold in this case. So these two conditions. Now we have to try to see what is the identity of element is there. Assuming that E is the identity element of this G, so by the property of identity elements, A composition E is equal to A. Now A composition E can be written as A plus E minus AE and is equal to E, and we have to write this is equal to, you have a E is common 1 minus A is equal to 0, and now because 1 minus A is equal to 0 and A is the element of a Q, A cannot equal to 1. So this means clearly only possibility is this E is equal to 0. So because A cannot equal to 1, so A cannot equal to 1. So E into A minus 1 minus A is equal to 0. So implies that E is equal to E is equal to 0. So identity element of this set is equal to 0. We can verify this, means A composition we have 0 is equal to, that is A plus 0 minus A into 0 is equal to A. So clearly identity element of this set is equal to 0. So 0 is belongs to Q, is also satisfy this. Now we have to check the inverse of this. So by the property of inverse is saying that if A belongs to G, there exists some B is element of a G which is inverse. If B is inverse of A, can be, it is equal to identity is equal to B composition A. So A composition B is equal to identity. Identity means you have a 0. So we can write A plus B minus AB is equal to 0. So now A plus we can write B times 1 minus A is equal to 0. And now since A is not equal to 1, so this can be written as a B times 1 minus A is equal to minus A. So if A is not equal to minus 1, then B can be written as a minus A upon 1 minus A is a defined, and this is again is a some rational number. So if A is the element of a set Q, then the inverse of this element is this, B is equal to minus A upon 1 minus A is the inverse of a this set. Now last condition we have to verify that A composition B is equal to, we have A plus B minus AB. AB, all are the elements of a rational number. This can be written in the form of a B plus A, because rational number under addition is a commutative, and also rational number under multiplication is commutative. We can write in this form. This is equal to B composition A is there. So A composition B is the same as a B composition A. So we satisfy all the properties of a group. So we can say that in this case this set of all rational numbers except 1 is an abelian group with respect to the binary operation, this thing. If the binary operation defined in this way, so this form a group. So let us try one more another example. We have to say that we take a matrix and we try to show that this matrix under multiplication is form a group. So let S is equal to A, all the elements of A is a real number except 0. So under multiplication, because we have to taking the multiplication, so if we have a 0 matrix, then under multiplication is inverses does not. So A we have to taking such a matrix where all the elements of this A are not equal to except 0, all are the real number. So we try to solve this problem, and we have to show that this as this set under the binary operation multiplications is form a abelian group. Let us start with the closure property. Let A take a two elements, A is equal to this and B is equal to this element of this set S. Then if we take a product of these is like this, AB plus AB, and then we have to 2 times AB, 2 times AB, 2 times, all are the elements of the same, 2AB, 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 and then if A and B are the real number except 0, so this means AB is also is a real number except this is also except, so we have a, also except 0, and this is also is a real number, and this is also real number. So this is clearly this set is belongs to the S, and then if this set is belongs to the S, then under multiplication of a tree, S is a closed, we can say that. So so first condition of a closed net is satisfied in this problem. Now next we know that the matrix multiplication is associative, so there is no need of we have to verify this again as associativeness. So we have to assuming that as a matrix multiplication is so S is a associative. Now we have to try to find the what is the identity element of this matrix. Assuming that E is equal to identity element, so E is equal to E, and E is clearly or belongs to the R but except 0, and then by the definition of identity we say that AE is equal to A by the definition of identity. So take any matrix A, we have a AAA and multiplied by this E, and this is giving you E, and then we have to multiply this 2AE is equal to, in this form is giving the AAA. So we have to simplify this matrix. We can simply say this implies that clearly 2AE is equal to A, and since A is not equal to 0, so we get E is equal to 1 by 2. So we have to A is not equal to 0, so we have to this just as that A is divided by this, so E is equal to, we have a 1 by 2. So E is a 1 by 2, that means matrix is E 1 by 2, 1 by 2, 1 by 2 is the element, is the identity element of a this matrix. So this case E is clearly we have to find the identity element of this set. Next we have to try to find what is the inverse of a element. So by assuming that A prime is equal to B B B, this, and by the definition of a inverse we can say that A prime is equal to identity is equal to A prime A. So we can just take a AAB multiplied by this identity element. We have a 1 by 2, 1 by 2 and 1 by 2. So if we multiplied this again, we have a 2AB, 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 and this is equal to 1 by 2. So again 2AB is equal to 1 by 2. We can just say that 2AB is equal to 1 by 2. Again, since A is not equal to 0, so B can be written as a 1 by 4A. So if A is the element of this set S, then the inverse of this is equal to 1 by 4A, 1 by 4A, 1 by 4A, 1 by 4A. So this means the inverse of this element is B is equal to this. So we can say that the inverse of any element of A is inverse is equal to, if A is the element of A, then the inverse of this is the 1 upon 4A, 1 upon 4A, 1 upon 4A, 1 upon 4 is this the inverse of this matrix. Okay, so now clearly this is trivial for commutativity conditions. AB is equal to, we have to 2AB, 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 we have to prove product is there, and now because A and B are the all the real numbers under the product of a real numbers are commutative, so we can say that 2AB can be 2FBA, BA, and that is nothing equal to product of a BA. So we can easily prove that if this set S is equal to the form of a AAA is a matrix form, and this is clearly S under the multiplications is an abelian group in this thing. Now this problem is we can say that prove or disprove that every group of order 3 is abelian. So that is an interesting problem. So we have to see we have a group of, we say that every group of order 3 is abelian. So take any group of order 3, since G has a order 3, so if G has a order 3, this means let G is equal to EAB, there is 3 types elements are there, where E is the identity element, and clearly if E is the identity element, so EA is equal to A, and that satisfies these conditions, and also E is the identity element, so this B with B is also is equal to this. So we take a cis group of order 3, which is assuming there is a 3 elements of this group EAB, and where E is the identity element. If E is the identity element, so with the E is giving you a and with B is also giving B. Now let us consider what AB should be equal to, because it is a group. So AB is closes also, so what is the value for A into B? So if AB is equal to A, if we are assuming that if AB is equal to A, then AB is equal to AE, but the cancellation is lost side that B is equal to E, and B is equal to E is a contradictions because B is not equal to E, so that means we clear a contradiction. Similarly, if AB is equal to B, then we can say that AB is equal to EB, and again by the cancellation law we can apply that EA is equal to the identity element. So again which is a contradiction is there. So that means we have a see that AB is not equal to A. Clearly AB is not equal to A, and AB is also not equal to B. The only possibility is this, we have a AB must be equal to E. So if AB is equal to E, then we can use the same argument. We can say that if AB is equal to E, then we have to, using the same arguments as above, we can say that BA is also equal to identity. So the only possibility, AB is equal to identity, BA is also identity, and we have every element. So thus AB is identity, B is equal to identity. So we can say that AB is equal to B of A. So this means hence in all products order does not matter, G is abelian. So we take this elements of G is equal to A, E is equal to A, B, so we have to identify this. So that means we have to prove that every group of order 3 is always an abelian group. So we have to move further. One more examples we have to try to let X be the set of X be any set and X be the set of bijections from X to itself. So we just said that S of X we have set into this form, and where F is a bijection. Now we have to just show that this Sx under the binary operation composition of a function is a group, and this is we have to just try to this. So let identity matrix, we have always identity matrix is a bijection matrix. So Ix be the, we assuming that the identity function of X is always is bijective. So Ix is the element of this, and then clearly S, this is clearly S is a non-empty. At least when we have to find that the identity function is belong to the this set S. So if identity is belong to the S, so clearly S is not a non-empty set is there. If identity function is there, this is working as the identity of a this set. Let F and G are two elements of this. We know that the composition of a two function by the property, if F is bijective, G is bijective, whenever a composition of a two bijective function is again bijective, we can easily prove that. So F composition C is also belongs to S. So means clearly if F is the bijection, then composition is F composition G is also bijective. This means is clearly this set is closed under the this composition of a composition function of two functions are there. Now composition of two function is always associative. We can easily prove that F composition G composition H is the same as a F composition G composition H. So associativity is hold for in general. So we have to simply say that this is satisfied in these conditions. Okay. Now we have to just say that F is the element of this Sx function is bijective, then its inverse is also bijective. So F inverse is also bijective. So F inverse is also the element of a this Sx, and now F composition, we know that F composition F is identity function. So we have to F composition F inverse is always giving the identity function. So this means consequently S over the this composition of a function binary operation is form a group. So if it is group, but this is a clearly is a non-abelian group. So we have to show that this is not necessarily commutative. For example, we take a X is equal to A, B, C. A, G is defined with F of A is equal to this, and then clearly we have to F and G are the two bijectives, one and onto functions clearly, and then we have to try to find the F composition G. So F composition G over B. So F of G of B is equal to C. F of C is equal to C is equal to C. Other way we have to composition G composition F over B. We can say that G over F of B is equal to, we have a G of A and G of A is equal to B. So F composition B is equal to, we have a C, G composition F over B is equal to B. So that means these two are not the same. So we clearly say that this is not equal to the same. So we can say that F composition G is not equal to G composition F over B. So for every B, so F composition E. So this means we can say that this set S under the composition of a two function is not commutative. So I have to stop here, and we have to cover all the portion of a groups. And now in the next class we have to start is a subgroups. We start with the basic definition of a subgroups and some examples, and then we have some important theorems of a subgroups is there. Okay, thank you very much.